right, let's talk a little bit about alkanes. The name of alkanes tends to be varied based on how many carbons are in the chain. Right now, we're just talking about straight chain alkanes, no branching. And since the only intermolecular forces are available are London dispersion forces, and if you're a little weak on intermolecular attractions, again, you can look at that video in the first semester course. The boiling points tend to increase smoothly as molar mass increases since there aren't really any other factors to consider. Methane to butane tend to be gases at normal pressures. Pentane to decane are liquids at normal temperatures. Each carbon has 4 single bonds. And what you find is that this is a homologous series because each time you insert the equivalent of a CH2 in the middle. And so here's the first 10 hydrocarbons. And so we find that methane is our first one, and it's CH4. And you see those boiling points are pretty low, -161. You don't have to memorize those, but it gives you an idea. Now, ethane is C2H6, or 2 CH3 units bonded together, and we'll talk about that just a little bit more about how these structures go together. But you can see between CH4 and CH3, there is the equivalent of a CH2 added, just not explicit like it is for the others. Go to C3H8, that's propane, boiling point -44, where the ethane was -89. You do see the explicit CH2 in there, so it's C3H8. Butane is C4H10, -0.5. Pentane is C5H12. Boiling point now is above room temperature, but still pretty low, 36. So we're talking about liquids now. Hexane, C6H14. Heptane, C7H16. You see the boiling point going up each time. Octane, C8H18. Nonane, C9H20. C10H22 is decane. You see each time the chain gets longer with a CH2 inserted. You really do need to know this list. You don't need to memorize the boiling points, but you need to know the rest of this table. So let's go to the paper and we'll talk about how to work with these just a little bit. So let's, for example, look at C3H8. And we said it had 3 units because the units coming together to draw the structure are 3 carbons. And we said that that would never be an outer atom. So we've got 3 central atoms linked together. And so where does some of this come from? Now, if I've got 8 hydrogens, where do the 8 hydrogens have to go? The carbon in the middle has 2 bonds and I need to get to 4, so it needs 2 more. The carbons on the outside to get to 4 bonds so that I can obey my octet rule needs 3 bonds. And so when I count the spots, 1, 2, 3, 4, 5, 6, 7, 8. So that corresponds to my 8 hydrogens. So the proper structure would look like this. Now, that kind of shows you what came from the table because there's a CH3 here. So that's CH3. And then the middle, CH2. And then you have CH3, where this is what we call a condensed formula, where this is your expanded. The expanded formula works when you're trying to show things when you're first starting, but showing all those hydrogen bonds explicitly in a very large molecule becomes cumbersome. Also notice the formula corresponds to where if N is the number of carbons, the number of hydrogens is 2N plus 2, and that's true of all normal straight chain alkanes. And so if you know the number of carbons, you can get the formula. Now you can also draw more of a line structure, and you draw it like so, and you draw that bend because it's tetrahedral. I don't draw any carbons or hydrogens explicitly on the structure, but it's implied that there's a CH3 there and a CH3 there and a CH2 there. You assume that you don't see anything else. There's carbon atoms with the requisite number of hydrogen. So this is our line model or line structure. Now let's do something a little bigger. Let's say we have, so if it's C6, 2N plus 2, that must mean it's going to be C6H14, which would be hexane. This one is propane. This one is hexane. So then I'm going to put 6 carbons in a row. 1, 2, 3, 4, 5, 6. So following the same pattern, the ends are going to get 3 and all the ones in the middle would get 2. Barring any other groups that we're still talking about normal straight chain alkanes. We put hydrogens on all the spots. If we count spots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So C6H14. And so you can see our nice formula works. If we want to condense that, we're going to have a CH3, right? Then we, in the middle, we get 1, 2, 3, 4 CH2s. And then a CH3 on the other end. Now, if we want to do the line structure, we need to count. So we go 1, 2, 3, 4, 5, 6. And so that would be our line structure. Counting again, 1, 2, 3, 4, 5, 6. So each end and each corner represents a carbon atom. And so that would be a good line structure for hexane.